Chapter 2. Deep Learning Essentials. 2.1 Deep Learning versus Traditional Machine Learning. Understanding the differentiation between deep learning and traditional machine learning is essential. Traditional machine learning algorithms are designed to learn from data in a linear or shallow manner, which involves manual feature extraction followed by the application of a learning algorithm. The features must be identified by an expert with knowledge of both the domain and the machine learning techniques suitable for the problem. Traditional algorithms such as linear regression, decision trees, and support vector machines rely on the quality of these features to make accurate predictions or decisions. They excel in scenarios where the relationship between input data and output predictions is not excessively complex and can be captured with simpler models. On the other hand, deep learning algorithms are based on the structure and function of the human brain, mimicking the way that biological neurons signal each other. These artificial neural networks consist of multiple layers of nodes or artificial neurons through which data is processed. Deep learning automates the feature extraction process, allowing the model to identify features and representations within the raw input data that might be less obvious or subjective to a human expert. This layer-wise hierarchical feature extraction is one of the keys to the success of deep learning, as it can uncover intricate structures in large datasets. Deep learning models are capable of handling unstructured data like images, audio, and text, which can be challenging for traditional machine learning models without significant pre-processing. For instance, to process an image using traditional machine learning, significant pre-processing might involve edge detection or texture analysis to identify salient features, and only then can these features be used for further analysis or classification. In contrast, a deep learning model would automatically learn to identify features such as edges, textures, and objects within the image through its layered architecture. The architecture of deep neural networks generally consists of an input layer, several hidden layers, and an output layer. Each layer contains a certain number of nodes or neurons, and each neuron in one layer connects to multiple neurons in the next layer. These connections, or weights, are adjusted during the training process to minimize the difference between the actual output and the predicted output. This complex interconnected structure allows deep learning models to represent nonlinear relationships between inputs and outputs, as well as interactions between features in ways that shallow learning models may not. Training deep learning models often requires large amounts of data and computational power. As the name suggests, deep learning models have many layers, some have hundreds or even thousands, which enable them to learn rich and complex representations of data. However, to train these models effectively, substantial data is needed to adjust the many parameters within the network without overfitting. Additionally, the training process can be computationally intense, as it involves forward propagation of inputs through the layers and backpropagation of errors to update the weights, repeating this process over many epochs to learn the underlying patterns in the data. The optimization of deep learning models also differs from that of traditional models. Deep learning uses backpropagation, an algorithm for efficiently computing gradient descent to adjust the weights of neurons. This process involves calculating the gradient of the loss function with respect to each weight in the network and iteratively adjusting the weights to minimize the loss. Unlike in traditional machine learning, where optimization techniques can be simpler and more direct, deep learning requires careful tuning of hyperparameters like learning rate, batch size, and architecture depth to ensure convergence and prevent issues like vanishing or exploding gradients. Another aspect where deep learning distinguishes itself is in transfer learning. Transfer learning is a technique where a model developed for one task is reused as the starting point for a model on a second task. For traditional machine learning, transferring knowledge can be limited and often requires handcrafted features to be fed from one model to another. Deep learning, however, can be particularly effective at transfer learning because feature representations learned by a deep network on one task can be somewhat general and thus useful for other, even dissimilar tasks. This leverage is mostly due to the hierarchical nature of feature extraction in deep networks, which captures universal features in early layers that are applicable across different domains. Ensemble methods combine multiple machine learning models to improve performance, and they are common in traditional machine learning. These methods, like random forests, which combine multiple decision trees, or boosting, which combines the output of multiple weaker learners, focus on improving the aggregate output with several models. While ensemble methods can be used in deep learning, the increased complexity and computational cost of training multiple deep networks make this practice less common as compared to ensembling simpler models in traditional machine learning. Instead, deep learning often involves fine-tuning single models with high representational capacity. Interpretability is a significant factor when comparing deep learning with traditional machine learning. Traditional models tend to be more interpretable, as the relationships between input variables and predictions are often more straightforward and can be directly translated into a human-understandable rationale. For example, a decision tree might split data based on clear binary decisions leading to an outcome. In deep learning, the complexity of the model and the large number of nonlinear transformations the data undergoes can make it difficult to understand the exact reasons behind specific decisions or predictions, leading to the characterization of deep learning models as black boxes. In conclusion, while both deep learning and traditional machine learning have their respective strengths and weaknesses, the choice between the two is usually dictated by the nature of the problem at hand, the complexity and volume of the data, and the computational resources available. Deep learning has become the go-to approach for many problems involving large-scale complex data, especially in fields such as image and speech recognition, natural language processing, and autonomous systems. Traditional machine learning, meanwhile, continues to be effective for problems where data is more structured or less voluminous, and where interpretability and computational efficiency are priorities. 2.2 Key Concepts in Deep Learning. Deep learning, a subset of machine learning, has at its foundation several critical concepts that enable the training and operation of neural networks. Neural networks are computational models inspired by the human brain that are capable of learning tasks by considering examples without being explicitly programmed to perform the task. At their core lies the concept of a neuron or a node, which is a computational unit that receives inputs, processes them, and produces an output. Similar to synapses in biological neurons, connections between artificial neurons carry a weight that adjusts as the neural network learns, effectively modifying the strength or importance of the input signals. Training a neural network involves adjusting these synaptic weights, usually through a process known as backpropagation. Backpropagation is an algorithm used for refining the weights of neural networks through a technique called gradient descent. During backpropagation, the network computes a loss function which measures the difference between the network's predicted outputs and the true values for those outputs. The gradient of the loss function, a vector of partial derivatives with respect to each weight, indicates the direction in which the weights should be adjusted to minimize the loss. By iteratively making small adjustments to the weights against the gradient, the network learns to predict more accurate outputs. The depth in deep learning refers to the number of layers through which data is transformed. Traditional neural networks might have just one or two hidden layers, while deep networks often have tens or even hundreds. Each layer can be thought of as a representation or abstraction of the data, with deeper layers providing more abstract representations. As data passes through each successive layer, the network learns hierarchical features, with higher-level, more abstract features building upon the lower-level ones. This structure enables deep neural networks to learn complex and high-level features from raw input data, which is particularly useful in tasks such as image and speech recognition. An important component in any deep learning model is its architecture. The choice of architecture depends on the specific task. For instance, convolutional neural networks, CNNs, are known for their performance on image-related tasks, while recurrent neural networks, RNNs, are tailored for sequential data such as time series or natural language. CNNs leverage spatial hierarchies and local connectivity by applying trainable filters that scan across input features and capture patterns such as edges and textures. RNNs, on the other hand, have connections that form directed cycles, allowing them to maintain a sort of memory by using their internal state, hidden layers, to process sequences of inputs. Another key concept in deep learning is regularization, which refers to techniques that prevent the model from overfitting to the training data. Overfitting is a common problem where a model learns to reproduce the noise in the training data so well that it performs poorly on new, unseen data. Regularization techniques such as dropout, weight decay, and data augmentation involve purposely introducing information or constraints to the model to reduce its complexity, forcing it to learn more robust and generalizable patterns rather than memorizing the training data. Optimization algorithms play a vital role in the training process of deep learning models, with stochastic gradient descent, (SGD), and its variants being the most common. These algorithms focus on finding the optimal set of weights for the network with minimal computational resources. Recent developments in optimization, like adaptive learning rates in algorithms such as ADAM or RMS-prop, help accelerate training by adjusting the learning rate for each weight individually, based on the estimates of lower-order moments of the gradients. This leads to a more efficient and stable convergence, especially in complex models and larger datasets. Activation functions introduce non-linearities into the network, which are essential for learning complex patterns in data. Common activation functions include the sigmoid, hyperbolic tangent, tanh, and rectified linear unit, ReLU, each having its advantages and disadvantages depending on the context of their application. Nonlinearity allows neural networks to make sense of data that is not linearly separable, facilitating the learning of complex functions. It is the stacking of these nonlinear layers that gives deep neural networks the capacity to approximate virtually any function given a sufficient number of neurons and layers. 2.3 Loss functions and gradient descent variance. Loss functions form a fundamental component in the training of neural networks. They provide a quantitative measure of the model's performance by calculating the discrepancy between the predicted outputs and the actual target values. The choice of a loss function depends on the specific type of problem at hand, such as regression tasks, classification problems, or more complex scenarios. A well-chosen loss function can greatly influence the convergence and effectiveness of the training process. One of the most common loss functions used in regression tasks is the mean squared error, MSE. MSE computes the average of the squares of the errors, that is, the average squared difference between the estimated values and what is estimated. This function is widely applied because it penalizes large errors more than small errors, which generally results in a more accurate model. However, one drawback of MSE is that it can be overly sensitive to outliers in the data, which might lead to distorted models if the data is not properly cleansed. For binary classification problems, a typical loss function is the binary cross entropy, also known as the log loss. This function quantifies the performance of a classification model, whose output is a probability value between 0 and 1. Cross-entropy loss increases as the predicted probability diverges from the actual label. It is ideal for models that output probabilities, as it provides a high penalty for confidently wrong predictions and a small penalty for less confident wrong predictions. In the context of multi-class classification problems, the categorical cross-entropy is utilized. It is a generalization of binary cross-entropy to multiple classes. In this case, the loss function assesses the difference between the predicted probability distribution across all possible classes and the one-hot encoding of the actual class. Categorical cross-entropy is known to work well with softmax activation functions, which often serve as the final layer in multi-class classification networks, by converting the output into a probability distribution. The hinge loss, commonly associated with support vector machines, can also be used with neural networks, particularly for maximum margin classification tasks. The objective of the hinge loss is to not only correctly classify all training data, but to maximize the margin between the data points and the decision boundary. This can lead to better generalization from the training data to unseen data, making the hinge loss an appealing choice for some applications. Beyond selecting an appropriate loss function, optimizing neural networks involves finding the right set of weights that minimize the chosen loss. This optimization is commonly performed using gradient descent algorithms. The simplest form is known as batch gradient descent, where the model weights are updated based on the gradient of the loss function with respect to the entire training set. While theoretically sound, batch gradient descent is often impractical for large datasets due to its high computational cost. Stochastic gradient descent, SGD, addresses the scalability issue by updating the model's weights using only a single data point at a time. This makes the algorithm much faster and able to be applied to large datasets. However, the trade-off involves an increase in the variance of the weight updates, which can make the convergence path noisier and potentially lead to suboptimal solutions. Despite this, SGD has proven to be an effective and popular method for training neural networks. To mitigate the noisy path towards convergence characteristic of SGD, mini-batch gradient descent is widely used. It represents a middle ground by computing the gradients on small subsets of the training data, known as mini-batches. This approach reduces the variance of the weight updates, which stabilizes the convergence path, while still being significantly more efficient than batch gradient descent. Mini-batch sizes are a hyperparameter, and choosing the right size is important for balancing the trade-off between convergence stability and computational efficiency. Adaptive learning rate algorithms such as Autodidact, RMSprop, and Atom enhance the performance of SGD by adjusting the learning rate during training. Autodidact adapts the learning rate to the parameters, performing larger updates for infrequent parameters and smaller updates for frequent parameters. RMSprop modifies Autodidact to resolve its radically diminishing learning rates. Atom, on the other hand, combines the advantages of Autodidact and RMSprop and is designed to be robust to the choice of hyperparameters. Each of these gradient descent variants has its strengths and ideal use cases. For example, Atom is often praised for its robustness in different scenarios and has gained popularity in various applications. However, no single variant can universally apply to all problems or datasets. It's critical that the chosen method aligns well with the specific characteristics of the problem at hand. Consequently, practical applications of neural networks typically involve trying multiple algorithms and tuning their hyperparameters to achieve the best results. As the landscape of deep learning continues to evolve, new loss functions and optimization algorithms emerge. Developing a deep understanding of these essentials, their strengths, limitations, and suitable applications is vital for anyone venturing into the field of neural networks. This understanding not only facilitates the effective employment of these tools, but also inspires innovation in the creation of custom functions and algorithms tailored to novel challenges in the deep learning domain. 2.4 Regularization techniques for deep learning. The pursuit of designing and training powerful neural networks necessitates understanding the concept of overfitting, which is a fundamental problem in machine learning. Overfitting occurs when a model learns patterns from the training data too well, including noise and outliers, and performs poorly on new, unseen data. Regularization techniques are critical strategies used to mitigate overfitting, thus enhancing the generalization ability of neural networks. This section discusses various regularization techniques, their implementation, and their impact on deep learning models. One of the primary regularization techniques is known as L1 regularization, also referred to as lasso regression in some contexts. L1 regularization works by adding a penalty to the loss function during training, proportional to the absolute values of the weights in the network. The penalty term is the sum of the absolute values of all weights, multiplied by a regularization parameter, typically denoted by lambda. The effect of this is to push the network towards sparsity, effectively driving some weights to zero and reducing the model's complexity. This can lead to simpler models that are less likely to overfit, and can often result in feature selection in cases where the input data has many features. L2 regularization, or ridge regression, is another commonly used technique. It differs from L1 in that the penalty added to the loss function is proportional to the square of the weights, hence encouraging small weight values, but not necessarily zeroing them out. The squared nature of the penalty tends to spread the error across all weights, and while it does not produce a sparse model like L1, it is effective in penalizing large weights. This means that L2 regularization can help prevent any single weight from having an outsized impact on the predictions, which can be especially valuable in deep learning models that are prone to overfitting due to large numbers of parameters. Dropout is a regularization method particularly suited for deep learning. During training, dropout randomly and temporarily removes nodes from the network, along with all of their incoming and outgoing connections. This forces the network to learn more robust features that are useful in conjunction with multiple possible random subsets of the other neurons. Dropout can be seen as training a kind of ensemble of networks within the same architecture, which often leads to better generalization. Importantly, dropout is only applied during training and not during evaluation of the trained model on new data. Early stopping is a different kind of regularization approach that contrasts with methods that modify the loss function. It involves tracking the performance of the model on a validation set during training and stopping the training process once performance begins to degrade or stops improving significantly. This prevents overfitting by not allowing the model to continue learning the noise in the training set once it has already captured the signal adequately. By focusing on the halt in performance improvement as a stopping criterion, early stopping is unique in its simplicity and effectiveness, even though it does not directly alter the model's complexity or its learning algorithm. Another technique, batch normalization, is often used to help stabilize and accelerate the deep learning training process. It works by normalizing the activations of each layer to have zero mean and unit variance, which is typically done before passing the activations through a nonlinearity. The normalization process also introduces a small amount of noise into each layer's inputs due to the mini-batch estimates of mean and variance, which can have a mild regularizing effect. However, the main benefit of batch normalization comes from reducing what is known as internal covariate shift, making the training process faster and more stable, and therefore allowing better generalization. Weight initialization strategies play a crucial role in the training of deep neural networks and can serve a regularization-like role. Careful initialization of weights can prevent layers from starting with gradients that are either too small or too large, reducing the chance of the gradients vanishing or exploding. Techniques like Xavier-Glorot initialization or He initialization are designed to maintain the scale of gradients throughout deep networks, thus helping in achieving convergence during training. Proper initialization ensures that the network begins training in a state more conducive to converging on a solution that generalizes well. Data augmentation is a practical approach to regularization that is especially useful in the context of limited training data. It works by applying random transformations to the training data, such as rotations, translations, and scaling, to create additional synthetic training examples. This can help neural networks learn invariances and robust features that are not specific to the training set, thus improving the model's capability to generalize to new data. Data augmentation effectively increases the size and diversity of the training dataset without the need for collecting new data, making it a cost-effective regularization method. The use of ensembles is another strategy where multiple neural networks are separately trained, and their predictions are combined, often by averaging or voting. Combining the strengths of diverse models can smooth out individual errors, reduce variance, and lead to better generalization on new datasets. Ensemble methods like bagging and boosting can be seen as a high-level form of regularization that operates across the predictions of several models rather than within the structure of a single model. However, ensembles also come with increased computational costs due to training multiple models, and they are not always applicable in real-time scenarios. Noise injection is a technique that involves adding random noise to inputs or hidden units during training. Adding noise can be seen as a form of data augmentation that encourages the network to learn to ignore small, irrelevant fluctuations. However, the strength and nature of the noise must be carefully controlled, as too much noise can obscure important signals in the data and degrade the model's performance. Noise injection should thus be tuned according to the specific problem at hand, and treated as a hyperparameter during the model development process. Penalty terms can also be introduced to constrain the activations of neural networks, not just the weights. For example, a penalty can be applied to the loss function to encourage activations to remain bounded, which can help in preventing the exploding gradients problem. This leads to constraints on the distribution of activations, promoting smoothness in the learned representations, and discouraging erratic or extreme activation values. Constraints on activations are often less common than weight penalties, but can be useful in certain architectures or problem domains. In deep learning, regularization is an important concept, as it helps neural networks to generalize beyond the training dataset and perform well on new, unseen data. As we've seen, regularization can take many forms, from L1 and L2 regularization, which penalize large weight values, to techniques like dropout and early stopping, which directly combat overfitting. Other methods like batch normalization and weight initialization strategies assist in ensuring stable and consistent learning. Data augmentation, ensembles, noise injection, and activation penalties further broaden the toolkit available to practitioners looking to train robust models. Regularization is thus a multifaceted discipline, an indispensable component of designing and training deep learning systems that achieve high performance across various domains and applications. 2.5 Backpropagation in depth. The backpropagation algorithm, often simply referred to as backprop, is a fundamental component of training neural networks. It refers to the method used for calculating the gradient of the loss function with respect to each weight in the network. This gradient is essential, as it guides the network on how to adjust its weights to improve performance during training. During the forward pass, input data travels through the network layers until it generates an output, which is then compared against the target value to compute the loss. The backpropagation algorithm is essentially concerned with what happens next, propagating the loss back through the network to understand the contributions of each weight to the overall error. Understanding how the backpropagation algorithm works demands familiarity with the concept of the chain rule from calculus, as it is the mathematical foundation upon which the process is built. The chain rule is used for finding the derivative of composite functions. In the context of neural networks, this means that if a network can be seen as a composite function of its weights and biases, then the gradient of the loss with respect to these parameters can be computed by applying the chain rule. This breakdown allows for the efficient computation of gradients layer by layer, starting from the output layer and moving backward, which is the essence of backpropagation. Backpropagation proceeds through several stages. First, it conducts a forward pass, wherein the data is passed through the network, and the output and loss are computed. It then follows a backward pass. During this backward pass, the gradient of the loss function with respect to the output of the network is calculated. This gradient serves as the starting point for applying the chain rule to determine the contributions of all the preceding layers to this initial error gradient. This iterative process involves computing the derivative of the loss with respect to the activation of each neuron, and then with respect to each weight. To facilitate backpropagation, neural networks use activation functions that are differentiable. This differentiability is necessary since the backpropagation algorithm requires computing the derivatives at multiple stages. Commonly used activation functions include the sigmoid function, the hyperbolic tangent function, and the rectified linear unit, ReLU. Each of these activation functions has its own set of advantages and plays a significant role in the efficiency and convergence rate of the backpropagation process. The learning rate is a critical hyperparameter in backpropagation. It controls how much the weights of the network are updated during the backpropagation phase. If the learning rate is too high, the network might overshoot the minimum of the loss function. Conversely, if the learning rate is too low, training may proceed very slowly and can get stuck in local minima. An optimal learning rate ensures that the network learns efficiently without oscillating or diverging during the training process. This hyperparameter often requires careful tuning, and sometimes adaptive learning rate methods like Autodidact, RMSprop, or ATOM are used to optimize this process. Backpropagation also involves regularization techniques to prevent overfitting. Overfitting occurs when a neural network models the training data too well, capturing noise along with the underlying data distribution. This leads to poor generalization to new, unseen data. Regularization methods, such as L1 and L2 regularization, dropout and early stopping, are used to penalize complex models and thus prevent overfitting. During backpropagation, these regularization techniques are integrated into the calculation of the gradients, effectively influencing the direction and magnitude of the weight updates. Weight initialization plays a crucial role in the convergence of backpropagation. Good initialization methods, such as Xavier initialization or He initialization, set the weights to values that neither vanish nor explode during the early stages of training. Poor initialization can lead to vanishing or exploding gradients, which significantly hampers the learning process. With correct initialization, each neuron is put in a position to learn optimally from the onset of training, which facilitates effective backpropagation through the network layers. The problem of vanishing and exploding gradients is more profound in deep networks with many layers. As the backpropagation process computes gradients from the output layer back to the input layer, the repeated multiplication of gradients can lead to these problems. To mitigate this, more sophisticated architectures like long short-term memory networks, LSTMs, and gated recurrent units, GRUs, have been designed for tasks like sequence modeling. These architectures have built-in mechanisms to allow gradients to flow unimpeded, ensuring stable learning even in deep or recurrent neural networks. Batch normalization is another technique that enhances the effectiveness of backpropagation. It normalizes the input of each layer so that they have a mean of 0 and a standard deviation of 1. This process helps to prevent the input distribution of each layer from changing too much, which is known as internal covariate shift, making the network's training more stable and faster. Batch normalization also has a regularizing effect, which can reduce the need for other forms of regularization. It must be noted that the gradients computed during backpropagation take this normalization into account, thus adjusting the weight updates in consideration of the normalized inputs. Finally, backpropagation's application extends beyond the standard fully connected neural network. It is also crucial in training convolutional neural networks, CNNs, and recurrent neural networks, RNNs. While the core principles remain the same, these architectures introduce specific elements like convolutional filters and recurrent states, which add complexity to the gradient computation. In CNNs, for instance, backpropagation efficiently deals with weight sharing that occurs in convolutional layers, ensuring that gradients are computed correctly for these shared weights. Understanding backpropagation is key to grasping how neural networks learn and evolve during training. The algorithm's iterative nature ensures that each weight update is informed by the most relevant information regarding how it will affect the final outcome. With backpropagation, neural networks can make nuanced adjustments to their parameters, enabling them to model complex functions and patterns within the data. This section has delved into the various components and considerations that make backpropagation not just an algorithm, but the backbone of how neural networks adapt and improve their accuracy over time. 2.6 Hyperparameter tuning and optimization. In the context of neural networks, hyperparameters can be understood as the settings that govern the overall behavior of the model architecture. These parameters are not learned from the data, but are set prior to the training process and have a significant impact on the performance of the neural network. Hyperparameters include learning rate, number of epochs, batch size, and the architecture of the neural network itself, such as the number of layers and the number of units per layer. Initial hyperparameter values are often chosen based on empirical evidence or heuristic methods, as there is no one-size-fits-all rule for setting them. Proper tuning of hyperparameters is crucial, as it can greatly enhance the model's ability to accurately generalize from the training data to unseen data. Hyperparameter tuning involves systematically searching for the optimal set of hyperparameters that results in the best performance of a neural network model. Conversely, inadequate tuning may lead to poor model performance due to overfitting or underfitting, where the model is either too complex or too simple for the given data. One common method for hyperparameter tuning is grid search. It exhaustively searches through a specified subset of hyperparameters, evaluating a model for each possible combination of parameters. This approach, while potentially effective for smaller parameter spaces, quickly becomes computationally infeasible as the number of hyperparameters grows. Grid search ensures a thorough examination of the specified parameter ranges, but may miss the optimal set if not finely tuned, and it does not scale well with the complexity of the model. A more efficient alternative is random search, which samples hyperparameter configurations at random for a fixed number of iterations. Random search is often preferred over grid search since it can search a larger space of hyperparameter configurations and is not limited to a grid structure. This method has been found to be more effective than grid search, particularly when only a few hyperparameters actually influence the performance of the neural network. The randomness in the search can often lead to discovery of good hyperparameters more quickly than the exhaustive approach. Yet another method that has gained attention is Bayesian optimization. This technique constructs a probabilistic model that maps hyperparameters to a probability distribution of the objective function, and uses this model to select the most promising hyperparameters to evaluate in the true objective function. Bayesian optimization takes into account past evaluations of the objective function, thereby potentially reducing the number of hyperparameter configurations that need to be evaluated. This approach is particularly useful when the evaluation of each configuration is expensive, such as with large datasets or complex models. Genetic algorithms and evolutionary methods form an additional class of optimization techniques for hyperparameters. These methods simulate the process of natural selection, where only the fittest individuals are selected to reproduce and hence pass on their characteristics to the next generation. In hyperparameter tuning, each individual can represent a set of hyperparameters, and their fitness can be evaluated in terms of model performance. Over successive generations, the algorithm converges to a set of optimal or near-optimal hyperparameters. These methods can be effective, but can be also computationally intensive and may necessitate a solid understanding of genetic algorithms to implement effectively. A contemporary and experimental approach to hyperparameter tuning is the use of reinforcement learning. In this paradigm, the tuning process is framed as a sequence of decision-making steps, where a reinforcement learning agent selects hyperparameters in order to maximize a cumulative reward, which is typically related to the model's performance on a validation set. The use of reinforcement learning for hyperparameter tuning is still in the research phase and is not yet widely adopted in practice, primarily due to its complexity and computational demands. The learning rate is among the most critical hyperparameters, and it controls the size of the steps that the optimization algorithm makes in the parameter space during training. A learning rate that is too high can cause the model to converge too quickly to a suboptimal solution, or to diverge altogether. Conversely, a learning rate that is too low may result in a long training process that might get stuck in local minima. Adaptive learning rate methods such as Autodidact, RMS-prop, and ATOM have been developed to adjust the learning rate during training, which often leads to better convergence properties. Another important aspect of hyperparameter tuning is the use of regularization methods to prevent overfitting. Regularization techniques such as L1 and L2 regularization add a penalty for larger weights to the loss function, which encourages simpler models that should generalize better to new data. A related hyperparameter is the dropout rate, used in dropout regularization, which controls the fraction of neurons that are randomly set to 0 during training, forcing the network to learn more robust features that are not reliant on any single neuron. Given the importance of hyperparameter tuning in constructing neural networks that perform well, there are several best practices that can guide the process. It is recommended to start with a small set of hyperparameters and models to understand their impacts on the performance. Once initial insights are gleaned, expand the search gradually to other hyperparameters while keeping computational constraints in mind. Visualization tools such as parallel coordinate plots can be immensely helpful in understanding the relationships between hyperparameters and the objective function. Efficient hyperparameter optimization is an ongoing area of research within machine learning. Advances in optimization techniques and computational resources will continue to refine the process of hyperparameter tuning. Given that the field is evolving rapidly, staying informed about the latest methodologies and tools will be crucial for practitioners. Moreover, the development of new algorithms designed to facilitate faster convergence and reduce the reliance on extensive searches will likely remain a prominent research avenue, helping to make neural network models more accessible and feasible in a variety of applications. 2.7 Introduction to Convolutional Neural Networks. Deep learning has emerged as a powerful subset of machine learning that employs algorithms inspired by the structure and function of the brain's neural networks. Among the various deep learning architectures, convolutional neural networks, CNNs, play a pivotal role, particularly in the analysis and understanding of image data. A CNN is a specialized kind of neural network that can capture the spatial hierarchy in data by applying convolutions, which makes it highly effective for tasks such as image and video recognition, image classification, and many areas of computer vision. CNNs differ from traditional neural networks primarily in their deep architecture and their method of processing data. While traditional neural networks process data through a series of fully connected layers where each input is connected to each output by a series of weights, convolutional neural networks take a different approach. A CNN processes data through a series of layers that are not fully connected, which include convolutional layers, pooling layers, and fully connected layers. This unique architecture enables the CNN to focus on specific features within the data at a reduced computational cost. In a convolutional layer, the network performs a mathematical operation called a convolution. Convolution is the process of applying a filter or kernel to the input data to produce a feature map. This filter is a small matrix of weights that slides over the input data, carrying out element-wise multiplication and summing the results to produce a single number in the feature map. The feature map represents specific features detected in the input, such as edges or textures, which are essential for understanding the overall composition of the visual data. Convolutional layers are often followed by pooling layers, which reduce the spatial dimensions of the feature map produced by the convolution. Pooling usually involves applying a function, such as max or average, to a subset of the feature map, and taking the maximum or average value as the output. This downsampling technique serves to reduce the computational burden and also provides a form of translation invariance, where the exact location of the feature in the input does not change the output of the pooling layer significantly. Following the stacking of several convolutional and pooling layers, CNNs typically have one or more fully connected layers toward the end of the network. The role of these layers is to take the high-level features constructed by convolutional and pooling layers and combine them to make a final classification or regression decision. The fully connected layers act much like the layers in a regular neural network, with each neuron in the layer connected to every neuron in the preceding and following layers. The training process for a CNN involves adjusting the weights of the filters as well as the weights in the fully connected layers, using a variant of gradient descent called backpropagation. During backpropagation, the network calculates the gradient of the error with respect to the network parameters and adjusts the filters and weights in the opposite direction of the gradient to minimize the error. With each iteration, the filters become more adept at capturing relevant features, and the network improves at the given task. To enhance the performance of CNNs and prevent overfitting, several techniques are employed. One common technique is the use of dropout, wherein randomly selected neurons are ignored during training. This prevents the network from becoming overly reliant on any particular neuron and encourages more robust feature detection. Another technique is data augmentation, which involves artificially increasing the size of the training dataset by making small modifications to existing data, such as cropping, rotating, or flipping the images. This exposes the network to a wider variety of features and situations, further strengthening its generalization capabilities. CNNs also utilize activation functions, much like other neural networks. ReLU, rectified linear unit, is the most commonly used activation function in convolutional layers, as it introduces nonlinearity into the model and allows for better performance and faster training. The ReLU function outputs the input directly if it is positive, and zero otherwise. This characteristic helps to alleviate the vanishing gradient problem, where gradients become very small and slow down the training process. One of the critical challenges in designing CNNs is selecting the appropriate architecture, which includes determining the number and size of the filters, the depth of the network, the size of the pooling layers, and how many fully connected layers to include. There is no one-size-fits-all architecture. It requires considerable experimentation and experience to find the most effective structure for a particular application. In practice, many researchers and practitioners will start with known architectures that have performed well in similar tasks and modify them as needed. Some well-known architectures include LeNet, AlexNet, VGG, GoogleNet, and ResNet, each offering different advantages and trade-offs in terms of accuracy and computational requirements. Advances in hardware, such as the increased use of graphics processing units, GPUs, for computation, have also played a significant role in the practical application of CNNs. GPUs are well suited for the type of matrix and vector operations that are fundamental in CNN executions. The parallel processing capabilities of GPUs have dramatically reduced the time required to train CNNs, thus enabling the use of deeper and more complex networks. CNN's impact on the field of computer vision is undeniable, and their applications extend well beyond image recognition. They are used in medical imaging for disease diagnosis, in self-driving cars for object detection and classification, in video surveillance for anomaly detection, and in natural language processing for handling sequences where spatial relationships can be leveraged. The continuous evolution of CNN structures and techniques promises further breakthroughs in areas where the interpretation of complex datasets is crucial. By effectively mimicking the human visual perception to some extent, convolutional neural networks have become indispensable tools for automated analysis in various scientific, industrial, and technological fields. 2.8 Introduction to Recurrent Neural Networks, RNNs. Recurrent neural networks, RNNs, are a class of artificial neural networks designed to recognize patterns in sequences of data such as text, genomes, handwriting, the spoken word, or numerical time series data emanating from sensors, stocks, and many other sources. Unlike traditional feed-forward neural networks, RNNs have connections that form directed cycles, thus creating an internal state of the network that allows them to exhibit dynamic temporal behavior. This internal state acts as a form of memory, enabling RNNs to use information from earlier in the sequence to inform later elements, which is a fundamental difference from other neural network architectures. RNNs are structured to reflect the sequential nature of their input data. While a feed-forward network processes each input independently, an RNN maintains a vector of hidden units that are updated recursively over a sequence. At each step in the sequence, the network's hidden units are influenced not only by the input at the current step, but also by their own previous state. This recurrent structure is key to the flexibility of RNNs in processing sequences of varying lengths, with the same network weights being applied to each step, making them highly efficient for such tasks. Developing an RNN involves several key architectural decisions. Input sequences can be processed in various ways, such as one-to-one, one-to-many, many-to-one, and many-to-many, depending on the task at hand. RNNs can be unidirectional, using information from the past to process future elements in the sequence, or bidirectional, where they process information from both past and future directions. Bidirectional RNNs are particularly valuable in applications such as language translation, where context from the entire sentence is crucial for accurate translation. The training of RNNs is carried out using a process called backpropagation through time, BPTT. BPTT is an extension of the standard backpropagation algorithm used in feed-forward networks, but it's adapted to deal with the sequential nature of RNNs. During BPTT, the network's errors are propagated back through each step of the sequence, and the weights are adjusted to minimize these errors. However, BPTT has limitations, as it can lead to vanishing or exploding gradients, problems that occur when the gradient values diminish or grow exponentially through the recursive process, making the network hard to train. To combat the issues of vanishing and exploding gradients, long short-term memory (LSTM) units and gated recurrent units (GRUS) have been developed. LSTM units include a memory cell that can maintain information in memory for long periods of time, and three types of gates: an input gate, an output gate, and a forget gate. Each of these gates performs a specific function, such as controlling the flow of information into and out of the cell or resetting the cell's memory. GRUS are a simpler alternative to LSTMs, combining the input and forget gates into a single update gate, and they merge the cell state with the hidden state, making them easier to compute and often faster to train in practice. A distinct feature of RNNs is their ability to deal with sequences of inputs that have varying lengths. This is made possible through the use of certain techniques such as padding, where sequences are padded with zeros until they all reach the same length, or bucketing, which involves grouping similar length sequences together. Truncating is another approach in which very long sequences are trimmed to a manageable length, although this technique may lead to loss of information for elements that fall beyond the cutoff point. When dealing with sequences of different lengths, it is crucial for a neural network to be able to handle them uniformly, and RNNs provide a particularly efficient solution to this problem. Another advantage of RNNs is that they can be used in a variety of sequence-to-sequence tasks. For example, an RNN can take a sequence of English words and generate a sequence of Spanish words, facilitating machine translation. They are also used for tasks such as speech recognition, where an audio waveform is converted into a sequence of phonetic units or words. Sentiment analysis is another application where a sequence of text is classified into categories such as positive, negative, or neutral. This adaptability to different sequence-based tasks has made RNNs a vital component in many natural language processing applications. Despite their strengths, RNNs also have limitations. One such limitation is their difficulty in handling very long sequences due to the vanishing gradient problem. As the sequence length grows, the gradients tend to become very small, causing the network to stop learning long-range dependencies. This is why LSTMs and GRUS, with their mechanisms for longer-term memory, are often preferred for tasks involving long sequences. Furthermore, RNNs are inherently sequential, which limits the parallelization that is possible during training and inference. This can lead to slower training times compared to other network architectures that can be fully parallelized, like convolutional neural networks, CNNs. Improvements and variations to the basic RNN architecture continue to be an active area of research. Attention mechanisms, for example, enable networks to focus on specific parts of the sequence when making predictions, improving the network's performance by allowing it to handle longer sequences with more relevant information. Techniques such as sequence-to-sequence learning, where one RNN encodes the input sequence and another decodes it to an output sequence, have also proved to be quite powerful, especially in machine translation and question-answering systems. Overall, recurrent neural networks represent a significant achievement in the area of deep learning, especially for tasks that involve sequential data. They are versatile and powerful tools that can capture temporal dynamics in data, but they also present challenges and opportunities for ongoing research. Innovations like LSTM units and attention mechanisms address some of these challenges, making RNNs more robust and applicable to real-world problems that require understanding and processing of sequential information. As research progresses, we can expect to see enhancements to RNNs that will further expand their capabilities and applications. 2.9 Introduction to Generative Adversarial Networks, GANs. Generative Adversarial Networks, GANs, constitute a class of machine learning frameworks introduced by Ian Goodfellow and his colleagues in 2014. GANs have since revolutionized the field of generative models, providing a powerful tool for generating new data samples that are indistinguishable from authentic ones. They have a wide array of applications, including but not limited to image and video generation, improvement of image resolution, and generation of realistic texts. GANs consist of two neural networks, namely the generator and the discriminator, that are trained simultaneously through adversarial processes. This adversarial training process is akin to a game, where both networks improve their functions while competing against each other. The generator network takes in random noise as input and produces data samples as output. Its goal is to generate new data instances that are similar to the authentic samples it has never seen during training. The generator learns to map the input noise to the data distribution of interest by continuously refining its output based on feedback from the discriminator. Initially, the generated samples may not convincingly resemble the authentic data. However, as training progresses, the generator improves its ability to create increasingly accurate and realistic outputs. Conversely, the discriminator network works as a classifier that aims to distinguish between authentic and generated data samples. It is provided with a mix of samples from both the authentic dataset and those produced by the generator. Its task is to assign a probability to each sample, indicating the likelihood of it being real or fake. The discriminator gets better at identifying generated samples by learning the characteristics that define the authentic data distribution. The discriminator's feedback to the generator contains information about the specific attributes of the data that lead to successful discrimination, which the generator uses to improve its output. During the training of a GAN, a minimax game is played out between the generator and the discriminator. The generator tries to minimize the likelihood that the discriminator will correctly identify its generated samples as fake, while the discriminator tries to maximize its ability to correctly classify both real and fake samples. The minimax game can be formally described by a value function VGD, which both the generator and the discriminator aim to optimize from their perspectives. This adversarial setup creates a dynamic where both networks continually adapt and respond to the strategies of the other. One of the critical challenges in training GANs is maintaining a balance between the generator and the discriminator. If the discriminator becomes too proficient too quickly, it can suppress the generator, preventing it from improving. This situation is often referred to as discriminator overpowering and can stall the training process. On the other hand, if the generator becomes too competent too quickly, it begins to produce samples that the discriminator cannot differentiate from authentic data, leading to a similar halt in learning known as generator overpowering. Ensuring that both networks improve in tandem is essential for the successful convergence of GAN training. Another challenge in GANs is mode collapse, where the generator learns to produce only a limited variety of outputs rather than a full-range representative of the true data distribution. This phenomenon is problematic because the generated data lacks diversity and does not accurately reflect the complexity of the original dataset. To combat mode collapse, various strategies have been developed, including modifications to the architecture, the loss functions, and the introduction of regularization techniques. Such strategies help to encourage a richer learning process that covers the distribution more comprehensively. The architecture of GANs can vary substantially, depending on the specific application and the nature of the data. For example, convolutional neural networks are commonly used in the discriminator and generator components when the target data is in image form. These convolutional architectures are adept at capturing the spatial hierarchies and patterns inherent in images. Various extensions and variations of GANs that tailor the architecture and training processes to specific tasks have also been proposed. These include conditional GANs, which incorporate additional information to direct the data generation process, and Wasserstein GANs, which propose an alternative loss function to improve the stability of training. The evaluation of GANs poses its own set of challenges, as traditional performance metrics used for supervised learning tasks, such as classification accuracy, do not apply to generative models. Common metrics for assessing GAN performance include the inception score and the Frechet inception distance, both of which rely on the properties of pre-trained deep networks to capture the diversity and quality of the generated images. Nevertheless, these metrics have their limitations, and no universally accepted standard exists for evaluating GANs. Additionally, qualitative assessments, such as visual inspection of the generated samples by human observers, play a significant role in the evaluation process. Research in GANs continues to be a vibrant and rapidly evolving area. Recent advancements focus on improving training stability, generating high-resolution and high-fidelity outputs, reducing the computational cost of training, and exploring new application domains. These efforts contribute to deepening our understanding of GANs and expanding their utility across various fields. The study of GANs intersects with broader research topics in artificial intelligence, such as reinforcement learning and unsupervised learning, creating opportunities for interdisciplinary innovation. In practical terms, GANs have fostered significant progress in creative domains, where they enable the generation of impressive artworks, music, and design elements. They also show promise in scientific and medical applications, where they can be used to synthesize data for research or augment limited datasets. Despite their potential, GANs raise ethical concerns, particularly in the context of deepfakes and misinformation, as they can be used to create convincingly realistic fake content. It is imperative to address these ethical dimensions, developing techniques that can detect generated content and establishing guidelines for the responsible use of GAN technology. Generative adversarial networks have come a long way since their inception, yet they continue to incite curiosity and research due to their powerful capabilities and open challenges. With every improvement in their architecture and training, GANs become more nuanced and potent tools for the generation of novel data. The future of GANs is likely to witness further integration with other AI domains, refinement of their architecture, and broader exploration of their ethical implications. The advancements in GANs not only enhance our capacity to create and innovate, but also deepen our understanding of the underlying complexities of data generation processes. 2.10 Leveraging pre-trained models and transfer learning. Pre-trained models and transfer learning are two key strategies in deep learning that have advanced the capabilities of neural networks significantly. A pre-trained model is a network that has been previously trained on a large dataset, typically on a general task, and has achieved reliable performance. Such models serve as an excellent starting point when developing a neural network for a related task. Transfer learning, on the other hand, refers to the technique of fine-tuning a pre-trained model to adapt to a new, but related problem. This process not only accelerates development time, but also reduces the computational resources required to achieve high-quality results. The advantage of using pre-trained models is most evident when dealing with complex tasks that require understanding of intricate patterns in data. For example, models pre-trained on ImageNet, which is a large visual database designed for use in visual object recognition software research, have developed a sophisticated understanding of features within images. These models can distinguish textures, shapes, and objects, among other elements. By leveraging these models, researchers and developers can benefit from the extensive learning that has already taken place, applying this deep knowledge to their specific image-related tasks with relatively minimal additional training. Transfer learning offers several practical benefits. It is particularly valuable in situations where labeled data is scarce or expensive to acquire. Since collecting and annotating data is often a resource-intensive process, being able to use a pre-trained model significantly lowers the barrier to entry for developing high-performance models. Additionally, transfer learning can reduce overfitting, as the pre-trained network has already generalized to a broad dataset, making it robust against noise in the new dataset. This use of pre-trained knowledge enables the fine-tuned model to make better predictions on the target task, given its foundation of learned features and representations. The typical process for applying transfer learning involves several stages. Initially, a suitable pre-trained model must be chosen based on its relevance and performance on a source task similar to the target task. The next step is to remove the original output layer of the model, which was specific to the source task, and replace it with a new output layer tailored for the target task. Following this, the model is trained, usually with a reduced learning rate, to allow the weights to adjust from the source task to the target task without large disruptions to the pre-learned features. It's crucial to determine how much of the pre-trained network to freeze, meaning the weights of certain layers are kept constant, and how much to allow to change during the fine-tuning process. This decision largely depends on the size and nature of the target dataset, and how similar it is to the dataset the model was initially trained on. If the datasets are quite similar, it may be sufficient to tune only the later layers of the network. However, if there are notable differences, it may be necessary to fine-tune more of the network's layers. From a technical standpoint, transfer learning modifies the parameters of the pre-trained model in such a way that they become more aligned with the features of the new dataset. The optimization process employed during transfer learning typically requires careful consideration of hyperparameters. The learning rate is often reduced compared to the initial training of the model, so as to make smaller changes to the weights. This reduced rate helps preserve the valuable knowledge the model has already gained, while still allowing for the necessary adjustments to new data. In practice, there are several commonly used pre-trained models available for tasks such as object detection, natural language processing, and more. Models like VGGNet, ResNet, and Inception have been pre-trained on millions of images and can serve as effective feature extractors for a wide range of visual tasks. In the field of natural language processing, models like BERT and GPT have been trained on large bodies of text and can be fine-tuned for tasks such as sentiment analysis, question answering, and text classification. While the benefits of transfer learning are significant, there are also challenges that must be addressed. One challenge is the potential for negative transfer, where the knowledge from a pre-trained model may not transfer well to a new task, potentially leading to worse performance than training a model from scratch. This issue often arises when the source and target tasks are too dissimilar, indicating a poor choice of pre-trained model or the need for more substantial retraining. Careful evaluation of model performance throughout the fine-tuning process is crucial to detect and mitigate negative transfer. Another aspect to consider is the ethical dimension of transfer learning. Pre-trained models may carry biases from their initial training data, which can propagate into the adapted model. It is the responsibility of the developers to ensure that the pre-trained models do not perpetuate or amplify biases when applied to new tasks. Measures should be taken to identify, understand, and address such biases during the fine-tuning process in order to develop fair and unbiased models. In conclusion, the strategy of leveraging pre-trained models and engaging in transfer learning is a cornerstone in the field of deep learning. It provides an efficient way to build upon previously learned knowledge, enabling the development of models that can perform complex tasks with a fraction of the data, time, and resources that would otherwise be required. Despite its challenges, transfer learning remains a dynamic and evolving area of research, offering vast potential for the ongoing development of neural network applications and technologies. As the field grows, continual refinement of these practices will be necessary to ensure their effectiveness, robustness, and fairness in an expanding array of domains.